We left off yesterday looking at these cross aldol Claisen reactions. I have not found a good resource. If you find one, let me know. I've not found a good resource that names them well. So it can look a little confusing because with aldol addition and condensation, we said an aldehyde or a ketone attacks an aldehyde or a ketone and gives a beta hydroxy carbonyl or an alpha beta unsaturated carbonyl. And then we said Claisen is when an ester attacks an ester and gives a beta carbonyl ester. So this, the cross aldol Claisen, I'm just giving it this name because we can interchange which groups serve which functions. Can you remind me yesterday what we looked at?
What, like the last thing? Or total?
The last thing.
Aldol Claisen cross reaction, and we went over LDH with
So I see. So we started with an ester. So we gave something that felt similar to an aldol. We said if I have an ester, I can attack a ketone or an aldehyde, and I can make an alpha beta unsaturated carbonyl or a beta hydroxy carbonyl. So that was our first example. Was an ester, and we turned this into an enolate completely so that it wouldn't do Claisen condensation with itself. And then we introduced a carbonyl, and I think I gave formaldehyde. And did I give a third step? Did I say we'll drive it to condensation or just heat?
HO minus plus heat.
Base and heat. And that's to drive the aldol addition, the beta hydroxy carbonyl, down to the aldol condensation. And I think I'm shorthanding the ester that I had yesterday a little bit. But here's that carbon from formaldehyde giving us the carbon, the beta carbon of the conjugated carbonyl. Okay, so esters can give us something that looks like aldol reactions, even though technically that wouldn't be what we consider it. And now we can reverse this. Why don't we take this aldehyde? We're going to do the same thing. First, we'll turn it completely into an enolate. So I'm going to react it with aldehyde. That way I don't get any aldol addition or aldol condensation reactions that proceed. And then I can introduce an ester. This time I think I'm going to do an acetate ester. This is methyl acetate. Yesterday we did a Claisen condensation with ethyl acetate, so this is very similar. And the nice thing about the Claisen reaction is I don't need to add extra heat or base to drive that condensation reaction. Reacting an aldehyde with LDA tells me that this is the nucleophile. The nucleophile is attacking from the alpha position. Introducing the ester second means this is the electrophile. The electrophile gets attacked at the beta position. So remember the product of a Claisen condensation is a beta carbonyl ester. Well, this is not going to be an ester. This is going to be a beta carbonyl because I'm not attacking with an ester. I'm attacking with an aldehyde. Here's my product. Alpha CH2 phenyl, alpha CH2 phenyl. Alpha bonds to beta. Beta has this leaving group. That ester leaves. That's the same thing we saw in the Claisen condensation. The ester linkage of the beta carbon gets eliminated. In aldol reactions, we do acyl addition to give a beta hydroxycarbonyl. And then we do simple elimination. Well, not typical elimination, but a new type of elimination. And we get an alpha beta unsaturated, conjugated carbonyl. In our Claisen condensation reactions, we have that acyl addition step followed by the elimination that reforms the acyl group, the carbonyl, which means overall, what I'm doing at the beta carbon counts as what type of reaction? Addition followed by an elimination equals synthesis. No. Good try that.
Substitution.
Substitution. So the example I was going to give you was, what would we call this? Where I take a carboxylic acid and I make an amide. I'm substituting at that acyl group. So this is acyl substitution. Same thing here. I'm substituting at my beta carbon OMe for this other carbonyl group. There's another thing that we can think of as acyl substitution, but we don't often call it acyl substitution. And that was all the way back in our reactions with aromatic rings. I substitute the chlorine of the acid chloride for an aromatic ring. That's acyl substitution. I'm also substituting a hydrogen on the aromatic ring for the carbonyl. So it's also aromatic substitution with an electrophile. It can serve both. This is a type of Claisen condensation, if you will, but in a much more relatable way, understandable way, it's an acyl substitution of the ester. That's all that Claisen condensation is. The nucleophile here is the aromatic ring. The nucleophile here is the amine. The nucleophile here is the enolate. All right. So I want to give you guys a chance to do just a couple of practice problems with this, decoding, retrosynthesizing products that we have. So that means that you'll need to identify the product that's present, figure out where the alpha-beta bond is, and break it to figure out the starting materials. Okay, came up with kind of a weird example on the right, because I think you can predict it to make two products. So those two products can be decomposed. like your thought here. I'll give you a hint. It's all going to fit in just one box. So rather than two products, just one. Actually, you know what? Yes, that would give you this product on the right. What you have here would give you this.
Yes, because prim, I could probably use that maybe. Or I could use that all day. Whatever, because there's only one option.
Exactly. That would work. But
Not for this one.
there is one starting material that actually could give you both of those groups. Do you remember how to retrosynthesize these? First, label what positions? Label alpha and beta. That can be challenging in some of these instances because you might not know what should be alpha and what should be beta. So sometimes that means there's more than one answer. Do you notice how alpha breaks its bond to beta, but it doesn't break its bond through the ring over to beta?
Right, so,
Oh. Remember what I like to do is sometimes stretch that alpha beta bond in the retrosynthesis and then cleave it and add the groups that you need to.
so that means that it has a ring there, right?
Yeah. Well, no,
Not a ring.
not a ring in the starting material, but all of those carbons in the ring are still connected in the starting material.
How does it get fused at the end? That's where I'm struggling with.
A base fuses it, where the enolate attacks it and stuff.
So it's in a ring?
Actually, there is a way to make the product on the bottom right with a ring, but you can't make both of them if you have a ring. And I wanted to take a look at this. Yes, good job. That does work. There's another answer too. I think I wanted to point that out for you. This works, but there is another answer. I think the same thing for you. This works and there's another answer. Yes, that works. And there's another answer. Oh, sorry, Caesar. You might have been the only one that didn't do that one.
I didn't do like that.
Which way did you do? Well, that's almost the same, except that you're missing your phenyl group here and you're missing the methyl group there. In your product, you're missing the methyl group.
You added that later. I'm just kidding. I missed it.
And then that just belongs there then too.
Okay, my bad.
And then your phenyl, your pH.
Where did I copy this from?
I don't know. I'm not sure. I mean, no, I mean you.
Oh, I copied it right. I just.
Yes, you were like 90% there.
Whoops. If you already have the anal
You can label alpha and beta on these. This one is much easier to label alpha beta. This one, which one do you decide is the primary carbonyl? That becomes more challenging. All right, so I want to give you guys that this product on the right can be synthesized from two separate reagents. If you have cyclohexanone and you react it with aldehyde, so you introduce it as an enolate, plus you have some sort of formate ester, meaning it's an aldehyde ester. Then cyclohexanone's enolate does acyl substitution on the ester and gives you this, carbaldehyde cyclohexanone. But there is one starting material that can react to give both of these products. So what we want to do is break apart those alpha-beta bonds. The unsaturated ester is actually the easiest one to break apart because it's really easy to label the alpha and beta there. On the bottom, it's harder to break it apart because there's two ways that you could label alpha and beta. You could label it like we did, alpha, beta, where the cyclohexanone's alpha carbon makes the aldehyde beta, or the aldehyde's alpha carbon makes the cyclohexanone carbon beta. Splitting it splitting the red alpha and beta takes this ring and then just makes it a chain. Whereas splitting the blue alpha and beta actually splits apart that one carbon of the aldehyde from the rest of the ring. Up here as well, if I split alpha and beta, I take a ring and I get just a linear chain. The information that we have actually tells us the linear chain precursor should have both an ester and an aldehyde. If the aldehyde acts as the nucleophile, it does acyl substitution on the ester, and it gives us a beta carbonyl. But if the ester acts as the nucleophile, if the ester acts as the enolate, then it does aldol condensation on the aldehyde. It gives us this. So either way you want to do this, my recommendation is to elongate an alpha-beta bond. So I'm going to try to show you this two different ways. Here's my elongated alpha-beta double bond. Remember in my retrosynthesis tips for aldol reactions, I told you give all of the hydrogens back to alpha and make beta a carbonyl again. So here's beta as a carbonyl, and that's 2 hydrogens back to alpha. That's my starting material. Does it look a little funky? Sure. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Or I could do something similar with this. I can, again, elongate that alpha-beta bond so that I can more clearly see how it breaks apart, and then split that alpha-beta bond. But in this case, I'm not retrosynthesizing an aldol condensation. So I can't say make beta a carbonyl. Beta was already a carbonyl. And I can't say give hydrogens to alpha. Well, alpha does, I guess, get 1 hydrogen. So in retrosynthesizing the Claisen condensation, I give that same tip of label alpha and beta, split alpha and beta. But the most important thing here is beta is an ester. So retrosynthesis of our beta carbonyl carbonyls, whether that's a beta carbonyl ester, whether that's a beta carbonyl aldehyde, a beta carbonyl ketone, when you've got a beta carbonyl from your carbonyl piece, the beta carbon is an ester carbon that just goes through substitution to become that ketone or that aldehyde. So this is my beta carbon. This needs to be an ester. That's the exact same structure. So the issue is I tried to give that cyclic structure at the top, and then I realized there's no way to selectively make the esters alpha carbon and enolate. If you're going to add, let's say, LDA to this reagent, both the esters alpha carbon and the aldehydes alpha carbon have a good chance of becoming the nucleophile. If the ester becomes the nucleophile, then I get something that resembles aldol condensation. If the aldehyde becomes the nucleophile, I get something that resembles Claisen condensation. Let's come back and apply some of this information about how do you do alpha-beta splitting in the retrosynthesis to find the other set of compounds that could make this product. Does anybody see it? The other way to split that product into two different starting materials? Here's what I see. I gave you this model, and I've been continuously giving you this model with Claisen type reactions, where the carbonyl on the right has the alpha carbon, and the carbonyl on the left has the beta carbon. And then you all just split that alpha-beta bond from right to left, and you get your ester, and you get your nucleophile. Why is this the primary carbonyl carbon? Why is this the alpha carbon, and this the beta? Can't... I didn't say so. You all gave the same retrosynthesis.
I get a different one.
Oh.
Sorry.
You're right, you did. And that is the other way to do this. So I'm going to label this one in blue. If I reference this as my primary carbonyl, then this carbon becomes its alpha carbon, and this carbonyl becomes the beta carbon. So when I split this, beta carbon is an ester, so I'm going to draw this as an ester. Alpha carbon gets one hydrogen back, and this is just whatever carbonyl is left there. The reagents are similar to each other. I've got this enolate, and I've got this ester. But the nature of them is very different. Methyl benzoate versus methyl propionate. 3-pentanone versus phenyl propanol. 1-phenylpropanol. Or you could call it phenyl ethyl ketone. Ethyl ethyl ketone, phenyl ethyl ketone. Two different ways to dissect it. That's not always true. Oftentimes, if there's an ester, there's only one way to dissect it and break it backwards. But when you've got just a ketone and an aldehyde, you often have two different routes. All right, so I'm going to give you guys one last task. In this example that I gave you before, we made this product. I want you to show me two different products two different starting materials that can be used in a very similar way to make that same end product. This one here. We made it using 3-phenyl propanal with LDA followed by methyl acetate. But I want you to find a different starting material that can react with LDA and a different ester. I'll give you that much. The second thing will be the ester. Yes, it is.
Is it? Okay.
Yeah. I think we just had it on the board.
Is it?
Yeah. You can name it. I know you
Yeah.
can.
Probably, if I really want to.
You know nomenclature is coming back on the
No, it's not.
nomenclature is coming back on the unit test.
Is it?
Yeah. We should do some examples then. Sure.
Is there nomenclature in the final then?
Is there nomenclature on the final?
Probably.
You know, one of the ways I enjoy putting nomenclature into the final is having like a reaction, and then I say what is the product of the reaction, but rather than giving you structures, I give you names. So not only do you need to know what forms, but you need to know how to name it. It's kind of a double whammy. I will say the nomenclature problems on the unit test are not incredibly challenging. Some of these would be more challenging than what I would give you. So maybe I'm going to give this an ET group, and we'll talk about how to name that as a refresher. And I like ethyl acetoacetate, but we could really name it itself. And then I think we'll look at naming that one too. So we'll do some nomenclature review. All right, who's feeling confident on this problem? What did you start by doing? Label alpha beta. That's the only thing I wanted to hear. Label alpha beta. And did you keep them labeled this way? No, because we've already done it that way. So what you should do from here is reassign the enolate carbonyl. This was the enolate carbonyl in our forward reaction. So now in this second reaction, this will be my enolate carbonyl. That still makes this alpha and this beta. Beta is what? Well, we have two types of synthesis tips. One of them is make beta a carbonyl. Beta's already a carbonyl. So our other retrosynthesis tip is make beta an ester. Make beta have a leading group. That's what we did before. We made this beta on the left an ester. So I'll make beta an ester. That's going to have a hydrogen on the left and an ester on the right. Caitlin looked at this before and said, does that exist? Yes, and we can name it. That name is what? For this ester, this one carbon methyl ester. Esters always have the alkyl name in front, methyl, and then they end with O8. Because this has a one carbon chain, that's methanoate. Methyl methanoate. But methanoate is systematic, it's not common. The one carbon carbonyl name. What is the one carbon carbonyl name? Form. Formaldehyde, formic acid, formate. So you could call this methyl formate or methyl methanoate. What is the other reagent then? Methanoate. Well,
No, it's 1, 2, 3.
because I cleaved alpha and beta, and I've already got this group, then it's just whatever else is left. One more time.
Phenol. Wait, that's not it. It's, which is the one, 5-phenol, 2-pentanol, 4-phenol, 2-1.
There's an issue actually with my synthesis, with this predicted synthesis. It's not the number of carbons. Actually has more to do with the base. LDA is our kinetic base, which means it's not going to deprotonate here to make this product. But OH minus isn't a strong enough base to give us complete enolization. NaOH is OH minus. Isn't a strong enough base to give us complete enolization. So if I did LDA, I would get a structural isomer of all of this. Now here's actually, this is a good exercise in saying, oftentimes your retrosynthesis gives you different possible routes. But not every route is equally as feasible. This is not a good route. This is a good route. That's okay. You can propose 2 different ways to break it, but one of them might actually be feasible in giving you the product. But we can still name this. See that you were trying. You can't just say phenyl though, because I need to know where along the carbon chain phenyl is. 4-phenyl. Keep going.
What's 4 again? Butanol.
Butanol. 4-phenyl, 2-butanone. But for the 4-carbon chain. Ane, because there's no alkene and there's no alkyne. One to indicate the ketone. Remember that suffixes have suffix stoppers. That's similar down here where I had methyl methanoate. It's not methanoate, it's not methinoate, it's methanoate. Which is odd because it's not like there's really any alkane in that carbon either. Now, to be fair, there is no other way to have butanone than to have it at position 2. There is no 1-butanone, because that's butanal. There is no 3-butanone, because that is 2-butanone, just numbered wrong. And there is no 4-butanone, because that's butanal. So if you gave this to me as 4-phenylbutanone, I would totally accept it. But it is really common to see butanone labeled with that 2. Let's do some more nomenclature. Can someone help me with this first one? What functional group is in it? An ester. So
So we need O8.
it's going to end with O8. And it's going to start with what?
So I
ET?
Oh, sorry. I was on the other side. Ethyl.
Ethyl. It's going to start with ethyl, and it's going to end with O8. O8 is the same suffix we give to carboxylates, benzoate, acetate. The difference here is it's not a carboxylate, it's alkylated. So it's ethyl O8. Longest carbon chain, prop. And there's a substituent methyl at position what?
2.
From the left or 2 from the right?
Oh.
True, but it's 1. It's from the right because the ester carbonyl is carbon 1. So ethyl, no hyphen, excuse me, ethyl 2-methyl propanoate. There is a weird common name situation with propane in that it's often named propianoate. Like they add in an I for whatever reason, and I'm not sure why. All right, let's keep going. What about this next one? What does it start with? Ethyl. What does it end with? O8, because it's an ester. You sure it's not going to end with one? No, ester is a higher priority functional group than one, than ketone. So how will the ketone be signified in this compound? What term do we use to label a ketone as a substituent? Oxo. And where is oxo on this carbon chain? It's at position 3 from the ester carbon. So ethyl, 3-oxo, 1, 2, 3, 4, butane O8, butanoate. What's another name for that compound? The common name that we've been referring to it as in our synthesis? Yeah, acetic ester. Ethyl acetoacetate would be its common name. Ethyl acetoacetate. So acetate, remember, is this. That's ethyl acetate. But that's not acetate. That has an acetyl 2-carbon carbonyl group attached to it. So it's acetoacetate. Terrible. Terrible, 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 terrible. It's fine though.
So what if
I don't have the
for that common name, we should change it if we have more carbons on that side, on the left side.
Yeah, you wouldn't be able to call it aceto
Okay.
if it had any more carbons.
Yes, aceto is that 2 carbons? Or what is it aceto?
Aceto is a 2-carbon with a carbonyl.
Okay.
The only time maybe you don't have a 2-carbon carbonyl is in acetonitrile. It's still 2 carbons, and this doesn't really look like a carbonyl. It's not a CO double bond, but a nitrile is considered part of the carboxylic acid derivative family by some people. So it's given a similar name. All right, what about my last one? What will be the suffix and suffix stopper? How will this name end?
With
Al for aldehyde and not one for ketone?
Yeah.
Why?
ANAO.
Yeah.
These are the aldehyde higher priority.
Yeah, aldehyde is a higher priority in the event that both of them are present. Why? Yeah, always prioritize having something at the front of a chain than somewhere within a chain. So an aldehyde is always going to start a chain. So I'm numbering from left to right. 1, 2, 3, 4, 5. So instead of anal, it's going to be pentanal. And what substituents will I have?
Phenol and oxo. No.
Phenyl, oxo,
Yeah,
methyl. Good. What order should those go in front of the name? Should it go 2, 3, 4?
4, 3, 2.
It's going to go 4, 3, 2. I should go highest number to lowest number?
Well, no.
Yeah.
I think that is the word.
I know, I'm just poking at you. It's going to go alphabetically, which in this case is methyl oxophenyl. Coincidentally, that is 432. It doesn't have anything to do with the locant number. Okay, so 4 methyl, 3 oxo, 2 phenyl, pentanal. Such a small molecule for such a long name. Okay, guys, it just crossed my mind that I forgot about another guy. He's a dick, though. I mean, a dickman. I think that's how you spell his name. I gotta be honest. I'll memorize a lot of stuff, but I have a hard time memorizing that. The Deichmann reaction is an well, you know what? We could call it, I spelled it right. Sorry. Instead of Deichmann reaction, we can actually clarify this better. We can call it the Deichmann condensation. This is terrible, in my opinion. This is an intramolecular Claisen condensation. So some guy got another guy's reaction named after him because he made it happen to make a chain. So let's say we have a compound like this. It's exactly the Claisen condensation, but it makes a ring. It's a little different than what we did earlier because that was a crossed reaction that had an aldehyde.
This one has
2 esters, yep. This is symmetric, so it doesn't matter which way I go. I'm going to have alpha attack beta. And now I'm actually going to pay attention to the numbers that I have here. So I'm going to call this carbon 1 attacks 2, 3, 4, 5, 6. I could react this with LDA, but that's more expensive and a little bit more challenging. I could really just react this with sodium methoxide, a base that matches the esters. That's going to make an enolate at either alpha position. They're symmetric. Alpha 1 attacks beta 2 and then comes together to make a 6-membered ring. And here's how I like to, it's just convenient to put carbon 2 beta on the top. And then let's say that carbon 1 is on the left-hand side. Carbon 1 attacked carbon 2, 3, 4, 5, 6, comes all the way back around. What else is carbon 1 attached to? The carbonyl of the ester. So carbon 1 over here also has my ester. Do you guys remember how this base serves in this reaction? I produce an equivalence of methanol, but that base is acting as what? catalyst. So the base is still present here. What's more acidic, the alpha hydrogen, carbon 1, in the beginning, or the alpha hydrogen at carbon 1 in the product?
Beginning?
More resonance at that alpha position in the product. So this doesn't actually sit here as a base, or sorry, as a product. This sits here as an enolate that is resonance stabilized. And so this reaction requires this aqueous workup. Now, the reason that I bring this up is because this enolate intermediate can actually control the regiochemistry of a unsymmetric Deichmann reaction. So I'm going to give us two examples here of products that can form. Notice the difference here is that one of the alpha positions has another methyl group on it. So the product on the left forms when that more substituted alpha acts as the nucleophile. And the product on the right forms when that less substituted alpha acts as the nucleophile. You guys see the distinction? Negative charge on this red alpha. Why is there no charge on that blue alpha? It doesn't have any hydrogens. A negative charge on that red alpha has a full octet too. But this doesn't have any alpha hydrogens to donate. Sorry?
4 bonds.
It does. It has 4 bonds, 2 atoms. None of those atoms are hydrogens.
I'm a little confused on why it ends up with that negative charge.
Okay. I'll just demonstrate over here real quick. After the Claisen condensation, this base, which is a catalyst, finds an even more acidic hydrogen and deprotonates it.
Oh, that's right. Okay, yeah, I guess I just missed that.
And that then is resonance stabilized, which is why we then have to protonate it.
Yeah, I guess that amino H wouldn't go there, would go on the other side, right?
It's not going to go to this side, less resonance. So it deprotonates.
No, I mean, your residue is like under that, so I thought it was there, but I guess,
Yeah, so a little confusing. Remember that this is a condensation reaction.
Right.
So an equivalence of methanol is condensed out.
Also, you get 2.
Well, this is a catalyst, and this is a byproduct.
Okay. Okay.
Good. So the catalytic base does a condensation reaction and kicks out methanol, but that catalyst then also takes an alpha hydrogen and locks it into this resonance stabilized enolate. So coming back to this idea, where one enolate gives this product that cannot be deprotonated again, and one enolate gives this product that can be deprotonated again. The issue in this reaction is that the beta keto ester isn't super stable. And so this can actually go through a reverse reaction. One of these beta carbons, this beta keto gets attacked by that methoxide, and it just reverses the reaction. But this product can't be reversed. It can't be attacked because it's an enolate. It is a nucleophile. So there's this really interesting feature of the Deichmann reactions where an asymmetric Deichmann prefers the product that gets locked as an enolate after it forms. So on the left, something that is reversible, not isolated. And on the right, an enolate that is irreversible and is the only isolated product. Well, okay, the enolate's not reversible after the acid workup.
Okay. I was gonna, so like on the test, if we have something like this, do we need to show like the final protonation step?
So it's a great question. What I try to do on the test, you talking about mechanisms or predict a product?
I guess either or, just where like, I don't know, do we just need to keep in mind like for these that like it will deprotonate like on its own, so then we should add in like, I don't know, protonation step after.
So on mechanisms, I'll make it very clear whether you're having a protonation step or not. I typically don't like to have mechanisms that have both basic conditions and then followed by acidic conditions. In a reaction roadmap, it'll be fairly clear whether I want you to give me this or whether I want you to give me something like this. I might not even have you guess at that, because it is weird. And the way that a lot of professors kind of circumnavigate around this issue of you should have a protonation step after is they'll just say, assume all aqueous workups as necessary. Grignard reactions, assume necessary workups. Reduction reactions, assume aqueous workups. Deichmann condensations, Claisen condensations, assume aqueous workups. I don't like to assume aqueous workups, but I'm also not trying to make this more cumbersome than it needs to be. But I do think that this is interesting. Before the aqueous workup, we can actually lock in this intermediate. And if we were to look at a reaction coordinate diagram, and we've got our ester here in the middle, what we're looking at is a product that is easily reversible, has a small activation barrier, doesn't give much stability, if any, and then we've got this other product that is irreversible, and that's this enolate versus just this beta carbonyl. I know that feels really complicated, but it's all to say these reactions can be regioselective. We don't have to worry about getting two different products. In my opinion, you very well might see a Deichmann reaction, and there's a better chance it's symmetric than asymmetric, which means you don't have to guess, am I going to the left or to the right? I don't think that your homework has any problems that make you go to the left or to the right either. So, all right, the last class of reactions that I want to look at, they involve this idea of conjugate addition. This is sometimes referred to as 1,4 addition, which is kind of funny because it doesn't look like 1,4 addition. The idea is that a conjugated carbonyl, and this is just generic, could be a ketone, could be an aldehyde, reacts with a somewhat weak nucleophile and it adds to the conjugate position. The reason it's called 1,4 addition is because the nucleophile adds to position 1. And then typically a hydrogen adds to position 4. The thing is, if a hydrogen adds to position 4, that means that there is a ketone that forms between 2 and 3, and that's an enol. And enols tautomerize back to their ketones or aldehydes. So it functions as 1,4 addition. Something adds to 1, something adds to 4. But it looks overall like something has added to 1 and something has added to 2. And that's why, in my opinion, conjugate addition is better. Now, the reason a weak nucleophile prefers to attack at position 1, there's an intermediate here that pushes the pi bond from 1 and 2. This nucleophile attacks position 1, puts that lone pair onto position 2. Nucleophile attacks beta, puts a lone pair on alpha. What is that? A lone pair on an alpha position? It is a nucleophile. What's the specific name for it? Enolate? That's an enolate. That is a negative charge on the alpha position of a carbonyl. That's just a resonance form of an enolate. And then this will react, often in an aqueous workup, to give us that final product. A strong nucleophile reacts in the same conditions to do 1,2 addition. So let's think of like our Grignards and our organolithiums. These are strong nucleophiles. So if I have the same condition, but I have something like a Grignard, my nucleophile attacks the carbonyl. So if I have methyl Grignard, my methyl group attaches to that carbonyl carbon. The weak nucleophile can't get to that carbonyl carbon just as easily. It actually prefers the beta carbon because the intermediate is lower energy. When you attack the beta position, the intermediate is resonance stabilized. When you attack the carbonyl position, the intermediate does not have any resonance stabilization. Okay, so one of the most common examples of conjugate addition is actually reactions with organocuprates. Let's take phenylcuprate, diphenylcuprate, and we're going to follow this up with an aqueous workup. The phenyl is the nucleophile of the cuprate. It attacks at the beta position, conjugate addition. And we'll compare that quickly with phenyllithium, followed by an aqueous workup. Which attacks at the carbonyl position. We already know this. What is that starting material's functional group?
Ketone.
Not good enough. Not detailed enough.
Conjugated ketone.
Conjugated ketone. How could you make that? How about aldol condensation?
Elimination.
Yeah, you could make an elimination, but stay in this unit. How could you make it using material from this unit? Well, that's an alpha-beta unsaturated bond. So I learned that we can just cleave that alpha-beta bond, make beta a carbonyl, and give the electrons back to alpha. Intramolecular aldol condensation. React this with aldehyde, and you can get your products. So the reason conjugate addition is coming up right now is because we just learned how to make these starting materials. So we can synthesize an alpha-beta unsaturated carbonyl, and then we can react that alpha-beta unsaturated carbonyl to do conjugate addition. Okay, there is a subset of conjugate addition, and it's called Michael addition. The idea here is that your conjugated carbonyl doesn't react with just any weak nucleophile, but it reacts with an enolate. Alpha attacks at the beta position and gives conjugate addition. Here's how I like to identify the functional group. This is not a beta keto carbonyl. This is not an alpha beta unsaturated carbonyl. This is not beta hydroxycarbonyl. The way that I like to identify this is what I called a shared beta dicarbonyl. Because you'll notice both carbonyls have the same beta position. The enolates alpha attacks the conjugate's beta. That makes an alpha-beta bond without breaking the original alpha-beta connection. Not a beta keto ester, not a beta keto ketone, not a beta keto aldehyde, but a shared beta dicarbonyl. So let's take an example where we first synthesize a conjugate carbonyl. I'll take this ketone, react it with LDA, then react it with acetone in the presence of base and heat to drive the condensation. I've made a conjugate carbonyl. And then I'll react this with another carbonyl. Now, I'm showing this as a carbonyl and LDA. I want you guys to recognize that if I'm adding this carbonyl and LDA, then LDA doesn't exist and that carbonyl doesn't exist. So I could have also just said, I'm adding this enolate. Now here's alpha. Here's alpha. I'm going to do this beta in blue and this alpha in blue. Here's beta. Here's alpha in blue. Beta had two methyl groups, but now it's bonding to that new red alpha. And there's my final product. If you want to look at it in a more normal configuration, you can see it there. Okay, now this really awful, horrendous thing happens with some Michael additions. And it's called Robinson annulation. But Robinson annulation is Michael addition followed by intramolecular aldol condensation. Robinson got this reaction named after himself for a reaction that was named after Michael. It's kind of similar to Deichmann getting a reaction named after himself for a reaction that was named after Clayton. So not all Michael additions have the conditions for an intramolecular aldol condensation. But some do. and this is not something that I will make you guess whether it has the conditions for it or not. This may show up in like a roadmap, and it will be obvious to you that it is going to run through. The interesting thing, actually, I don't think I usually put this in a roadmap. I more often have it as a multiple choice problem. The interesting thing about this is that the Robinson annulation is spontaneous. It doesn't require additional steps. It is simply the fact that the Michael addition will generate byproducts that push the aldol condensation. So we're going to try and do an example. Ready? So here's our Robinson annulation. I have a conjugate carbonyl and an enolate, and I end with a conjugate carbonyl. So I've done Michael addition. That has taken these two units and linked them together, and then I've followed that with an intramolecular aldol condensation. 2 units to create one longer chain that comes back and cyclizes on itself. Let's do a reverse synthesis. What can this conjugated carbonyl come from? Well, here's alpha, here's beta. I'm simply going to split those two apart. Beta becomes a carbonyl. What kind of functional group is that? Is that a conjugated carbonyl? Is that a beta keto carbonyl? What's the best way to identify that compound? It's on the board in red.
Shared beta dicarbonyl?
That's right. What'd you say?
I just said it really sarcastically.
Alpha, alpha, shared beta. How do you make a shared beta dicarbonyl? Michael addition, where alpha attacks beta that is connected to alpha. Now in this case, I've given us compounds that are very symmetric, so it wouldn't really matter which one you called what atom. You could break this Michael addition product in 2, and there are, for most Michael addition products, there are 2 different syntheses that get you there. Michael addition to the shared beta dicarbonyl, and then that shared beta dicarbonyl reacts where this becomes alpha and this becomes beta, and it gives you an aldol condensation. if there's really anything that I want you guys to take away from this class this semester, it is the ability to dissect a molecule and put words and descriptions to what's going on. Because even if you don't remember the names of the reactions, even if you don't remember what products are possible from different reactions, I think that if you can dissect a molecule and say, this region is partial positive, this region is slightly acidic, this region is partial negative, this region is slightly basic, those are the things that guide the reactions. I want you to be able to look at something and say, would there be resonance stabilization if this attacked at a certain spot? Because resonance contributes a lot to this semester. So being able to look at a molecule and say, where is resonance possible? Where is resonance not possible? Those are important things. Okay. I know that we don't have a lot of time yet. What I'm going to try and do is give us a practice problem to look at. I'm going to, if nothing else, try to point you in the right direction to practice this material outside of active, where there are practice problems for you. On our Canvas modules page, I want you to come down to the old 2320 materials. Come down to enols and enolates. Or keep going to the supplemental problems, where you'll get twice as many of these examples. This gives you problems for working on electron arrow pushing. Not all of them are mechanisms that I'm expecting you to show in the unit test or the exam. Has you predict aldol addition, aldol condensation, Claisen condensation. Gives you practice problems with a roadmap. Where is it? This is on our modules modules page. It's towards the bottom. It is the second to last module. Problem sets and supplemental work sets.
Why do they have frowny faces?
They're not accessible.
I know it doesn't show on our side, but
Yeah, it's about the materials not being accessible. Yeah. Okay, so there's some retrosynthesis problems here too. I want to see if we can do this one together. First, identify the functional group that's here.
Which one are we doing?
D, the last one. Give me more.
shared beta dicarbonyl.
Is it? Is it a shared beta dicarbonyl? Is it a dicarbonyl?
Yes.
Then why'd you give me ketone?
There's the
You could have given me diketone. It's not just a ketone. And then you could have told me whether they were beta ketones. Was one ketone beta to the other ketone? They're not. Alpha, alpha, shared beta. So how could I make this? That's what this arrow means, is retrosynthesis. What are my possible products here? Or excuse me, what are my possible starting materials? Let me ask this. This is a retrosynthesis. What reaction gives me a shared beta dicarbonyl product? Good. It's on the board for you. And what reagents are involved in a Michael addition reaction? Conjugated carbonyl and an enolate. So one of these carbonyls needs to be a conjugated carbonyl. Do you care which one? Which one? We'll make the one on the right the conjugated carbonyl. Here's its alpha and its beta. That means the other carbonyl is the enolate. The enolate makes the bond to the conjugated carbonyl. So I need to break this bond. That's my enolate. And it's going to attack my conjugated carbonyl. Is that the only way to make this final product? What do I have to do to find the other set of starting materials?
Switch which one is conjugate and the other.
Switch which carbonyl comes from the conjugated carbonyl, and which carbonyl comes from the enolate. Now, in the real world of synthesis, this might actually look like one set of starting materials, super easy to get your hands on, and the other set of starting materials, much harder to get your hands on. So there's an idea of feasibility in the real world here. But on paper, two options. Pick your poison.
I don't know that. Sorry, I'm not going to explain this, but if I have a beta shared carbonyl like that, bicarbonyl like that, I don't know, it's not going to go into Robertson English.
Yeah, it often can.
Obviously it can.
Yep. So there's not a good answer for you there.
Oh.
I will say this: if you use LDA to do to make the enolate, then you probably won't immediately go into Robinson annulation. But if you use hydroxide to make the enolate, that means hydroxide acts as a catalyst, and it can make another enolate out of this. So it's kind of your condition. LDA doesn't automatically run towards Robinson. Hydroxide will. If you're using hydroxide to make this enolate, hydroxide will catalyze the next step of the reaction as well. We have an OChem2 experiment that we don't run anymore just because there's not enough time in the semester. And in that experiment, we do a Robinson annulation. It takes 5 minutes. You take a conjugated carbonyl, and you take another carbonyl, and you add hydroxide. An enolate forms, Michael addition happens on the conjugated carbonyl, and then that hydroxide catalyzes the Robinson annulation as well. It happens very quickly.
So let's say we get these two products. If you put hydroxide in that area, we will know that we want the Robinson annulation.
Yeah, you know what I would say more so is show me the Robinson annulation product that forms rather than having you guess. I do something similar with aldol addition versus condensation. It can be very hard to know which one is expected to be shown. So I try to give clarity there. Show me the aldol condensation. Show me the aldol addition product. On your unit test, you are going to have to do a multi-step synthesis. But this is not something that should feel confusing to you. It should feel very similar to what we've been doing this whole time with Aldol, Claisen, Michael, Robinson. You're also going to have to do mechanisms, and your mechanisms are the aldol addition, aldol condensation, or Claisen condensation. And I just want to be clear, Claisen condensation and aldol addition are less steps inherently than the aldol condensation reaction. So I want you guys to know, aldol condensation doesn't usually ask you for resonance. It says you do not have to show resonance. But the aldol addition and the aldol condensation, it explicitly asks you to show all resonance forms of your enolate. What I'm doing there is adding more steps in to those shorter mechanisms so that they are the same number of steps of the aldol addition. That way I can assign the same number of points to everybody's mechanisms. Otherwise it becomes really messy on saying Matt got a 10-step mechanism and Roth got a 5-step. How do I grade with the same number of points for those? So I want you to pay attention to those bullet point lists that I put there. If it asks you for resonance, make sure you show resonance. Okay? Not challenging mechanisms by any means, just maybe a lot going on with the structures. Okay, guys. Good luck on your unit. That's it. That's our whole semester. We can talk about amines on Tuesday if you want, but I'm not going to put them on the final. I mean, you will see amines in some regard because we talked about reduction of nitriles, reductions of amides, reactions to make amides, but we're not going to look at the chapter on amines. Good luck on your unit test this weekend. Come in on Tuesday ready for a review day for our final on Thursday.
So on the final, is it just going to be synthesis from the last 2 units, nothing from the first ones, or should we also like?
The final will have mechanisms from the last 2 units.
Yeah, that's what I meant to say. I don't know what I said.
The roadmap synthesis will have the whole semester in there.
Okay.
You could see
mechanisms just this second half.
correct. You could see NAS, EAS, oxidation, reduction, all sorts of stuff on the roadmap and in the multi-step or in the multiple choice section.
We are still the same page, or we get multiple pages?
2 sheets,
Yeah, two, right?
or sorry, 2 pages. So like 1 sheet front and back. I feel like I'm saying that wrong. 2 sides, 1 sheet front and back, where I have a lot of people that want to do 1 side of 2 sheets. I even had one guy last fall that said, I did the math, and if I take 7.5 note cards, front and back, it's the same amount of surface area. And then he organized it by unit or by chapter or something.
Oh,
So he didn't like glue it all to a sheet of paper, he just had note cards with him. So if you want to do that, you're welcome to. But you get twice as much space as what you did on the midterm. If that makes sense. All right. Have a good weekend, guys. See you Tuesday.